on radio. Tonight, Dr. Frank Lynn's going to be talking about software-defined radio. Dr. Frank Lynn has a bachelor's in physics and computer science from University of Washington, a PhD in geophysics also from University of Washington, and now works as a research engineer at MIT's Haystack Observatory. He also is an IEEE member, a member of the American Geophysical Union, and the former U.S. National Committee chair for the International Union for Radio Science.
Commission on Ionosphere and Radio Propagation. So. Not the whole thing.
With that, I'd like to welcome Frank Lynn.
Thank you very much. So thank you very much for the invitation to speak here today. I appreciate it. Radio is what I do, and I've been doing this for a little too long now. But in any case, today I was asked to talk about software radio, and software radio has really been a thing here that we've been using at MIT Haystack, and it's been transforming beneath our feet, I would say. It's literally a revolution that's been going on since the late 50s and early 60s, and it's progressing to the point where I would call it the democratization of radio is upon us, and we don't know what to do. And so I'll talk today about software radio. I'll give you some background on it. I'll talk about some of our work that we've done related to it. I'll show you software radio systems. I have a little bit of a demo of some inexpensive software radio you could probably go afford to purchase. Some of you who have budgets can purchase the more expensive software radios potentially. But I'll sum up kind of with some of the things that are interesting me in the application of software radio scientifically. So I work at MIT Haystack Observatory, which for those, you're seeing a number of people from Haystack in this series, so you've probably been introduced to it already. We're about 43 kilometers as the radio wave goes from where we are standing now, plus or minus, a few kilometers. And
we need the light for you.
Oh, you need the light for me. All right. We do radio science. We do radio astronomy, space surveillance, satellite imaging. We do geospace science, the study of the space environment, and underneath it all are also developing fundamental techniques. And the complex has a number of radars and radio telescopes, and since this is not a tour of Haystack, I'm not going to go through them all. I have spent a lot of my career nursing along the UHF radar system and using it to do science, as well as more recently I'm working with pretty much all the systems at Haystack at one level or another. There's a combination of MIT campus, academic research, and MIT Lincoln Laboratory defense research facilities at Haystack, and we work jointly together. It's actually relatively seamless in general, and it does make for interesting meetings, though. Underneath software radio is a desire to be able to manipulate and use the electromagnetic spectrum. And radio, is a slice of the spectrum. We normally operate for human beings in the regime of visible light, which is this little sliver of the electromagnetic spectrum. And radio waves actually occupy a significant chunk at wavelengths that are fairly significant. They're interesting because they're actually comparable to human beings in wavelengths. And there has been a progression as time has gone on from being able to manipulate light and radio waves at very long wavelengths and progressively going to shorter wavelengths. And this, combined with digital technology, has given rise to the ability to really utilize the electromagnetic spectrum as a function of frequency and to chop it up into bands, as we call them, and to use those bands for various applications. And if we started from scratch today, I don't think we would do this. I think we might treat things very differently, and there's been kind of efforts to try to get people to think about that and to make radio systems that are agile and jump around. And software radio is behind the ability to do a lot of that, but it really behooves us to think in the future about different methodologies of using the radio spectrum. Now, the radio spectrum's also interesting from the point of view of the Earth and looking out in the space environment, in that when you look through the Earth's atmosphere as a function of wavelengths here and how opaque the atmosphere is, we have a visible light window. There are some infrared windows. There are microwave windows, and then there's a radio window. And then down at the lower frequency end, the Earth's ionosphere eventually cuts you off because of the plasma frequency in the ionosphere, and so the radio waves from space don't really get to the Earth very effectively, and radio waves from the Earth at low enough frequencies don't get into space very effectively. Manipulating the spectrum, it used to be very complex and hard, and now it is becoming easier and easier and easier in many ways. On the other hand, we're trading complexity in devices and hardware often for complexity in software. And so it isn't as simple a trade-off as analog radio old. If you're doing analog radio, you belong in the 20th century or something like that, right? I can say that now, it's the 21st century. But, and if you're doing digital radio, software radio, you're doing the modern thing. But there's actually a merger of both, a role for both, and I think that the combination, it remains to be explored how to make software radios, say, very power efficient, for example. So I'll talk about that. Early analog radios. Okay, so when we think about analog, we think about illustration here. Somebody figures out, I can make a diode, and I can do really interesting things with a diode. And it literally started with experimentations with crystals and the underlying physics. And if you were a precocious lad in the late 19th century, and you were somewhat wealthy and able to spend your time how you wanted to, maybe you spent your time playing around with these interesting ideas about electricity,
I'm going to label that.
There was a person, of course, Marconi, who did that. And in 1895, at the age of 20, he demonstrated the Marconi monopole, which is
we might as well use the right number.
As we would think of it of modern radio, I would say. And that's actually, how much have we done by the time we're 20? Our society kind of biases us to study, do different things, go to school, and there's maybe less room for people to be innovative there. But then we went on to having things like the crystal diode radios very shortly thereafter. Regenerative receivers, which was Edwin Armstrong was behind that. And this is really the path that led to FM radio as we see it today. That's the Armstrong super heterodyne. And listeners get an earful by radio. So radio was the early subversive way of breaking the communication of newspapers and tabloids. And it was the new thing at one point. And today, I think
just remembering that it came up
revolution, radio
as if it had stood still in 1987, never having questioned how the Chinese buffet remained open, save for the steady stream of traffic that came through. But rarely did anyone investigate the rest of the strip mall that rested in every more space of decay.
You could buy a radio receiver that would tune from half a megahertz to 30 megahertz for the bargain price of $105. All right? And today, if you do the inflation calculator, it comes out to about several gigahertz, and it's $15. So we've seen a change in absolute terms in the complexity and cost of these systems, and that change is in many ways just getting rolling. It's been an ongoing process. There have been a number of steps in the complexity and the cost of the radios and in their performance they offer. And it's been coupled one-to-one recently with the development of computing. And, people always say, I have a colleague who always says, it's $15, Frank. And I go, yeah, plus the $1,000 computer you're hooking into. So it's really $1,015 or a few $115 if maybe you're using a Raspberry Pi. Maybe you can get it down under $100. But we are headed for the era where you have the $1 software radio, I think. So analog radio receivers are really, their evolution, as I said, went from low frequencies to now all the way up into terahertz. And they go from spark gaps to tubes to transistors to integrated circuits and now nano devices, quantum lasers of various kinds, integrated masers that you might etch out in the lab to get you into terahertz. And there's all kinds of interesting things that have been opened up by this progression, which took us from, VLF, very long wavelengths, into HF, which that brought about transistors transatlantic propagation and communication, and a revolution in things, you could have a ship, and if it was in trouble, it could send out a distress signal with Morse code. And then, gradually we moved up. There was kind of, in World War II, a shift up above HF and into UHF and L-band, and then very quickly to X-band. And more recently, we've seen a shift to higher frequencies like W-band, which we have a radar at Haystack that operates there. And you saw receivers fundamentally transform, and a lot of the transformation was about achieving frequency selectivity.
Blockchain technology can play a pivotal role in the secure and transparent handling of this data, ensuring privacy and integrity.
Both because that's how we decided
Potential
to manipulate
income
the
and
spectrum and allocate it. So
contribution to
government allocates it
humanity's
in chunks,
future.
and it does it in terms of frequency. And in terms of spatial location
The
and
integration of blockchain and cryptocurrencies opens up new revenue streams for the online shop, from transaction fees saved through decentralized payments to potential income from content shared on platforms like STEMIT. Moreover, this model can contribute significantly to humanity's future.
It is never required to prove his innocence, nor does the defendant ever have to produce any evidence at all. Second, the state must prove the alleged crime beyond a reasonable doubt. A reasonable doubt is not a mere possible or imaginary doubt. It is a doubt based on
and amplify and provide some level of improvement in the signal-to-noise ratio that was being experienced by the audio listener. And early on, this was all audio. It was all listening and people listening on headsets. And these days, we listen with computers, and often we have the machines doing the listening these days. Instead of the human beings doing the listening. But, we have regenerative receivers was part of the progression. And then the super heterodyne was really where Armstrong came in, and you had an absolute transformation in our ability because we substituted in this local oscillator and a mixer. And that allowed us to very easily vary this local oscillator and translate a selection of RF signals in through a filter that then could be fixed. And so you weren't having to make custom filters for each frequency you were wanting to manipulate or listen to. You were able to use that local oscillator in order to select a band of frequency. And then, you put it through your audio detection and your amplification, and you lo and behold, you had radio. And of course, you can make these more complex. You can have multi-stage super heterodynes. You can have up-down converters. You can do all kinds of clever things. And, this is a wonderful way to do radio, actually. I have to say, I've built many of these types of receivers over the years, and we use them often to limit the complexity of the digital receivers. Of the software radios, to limit the bandwidth, to improve the selectivity of a digital system by adding an analog system in front of it that has performance characteristics that are better for the particular task. Now, these do have a disadvantage. They tend to be physical devices. They tend to be larger. Of course, everything's miniaturized, and we have lots of wonderful circuitry now. You can just go on the web and find any mixer you want that has wonderful performance and low-noise amplifiers that are incredible. And, it's this golden age of components and parts and the ability to put together almost anything you want. But they do take space. They often use power, so you will end up with energy dissipation in these circuits. That's often actually a lot less energy dissipation than you will have in a equivalent digital process that does the signal processing equivalent of these stages. They also, importantly, I think, exhibit variability. So your filters can drift. If you have a very narrowband filter and its response drifts as a function of temperature, and you're in a place where the radio has to operate over a range of temperatures, it can be very difficult to
it's going to be a dirty word.
Tune that
out unless you have a human being
sitting there tuning a dial. Sometimes you have
people
systems
get
that need to be calibrated, for example.
I can't do that. I took that trigonometry in school.
Also, if you want to change your filter bandwidth, well, you need either a filter that can be changed in bandwidth, or you switch between different filters, and that frequency selectivity, all of a sudden I'm multiplying out the physical size of my system and the complexity and the number of things that need to be calibrated. So this variability was important. Another thing that is important is the detection circuitry. Initially you're working with various kinds of modulation. So you're attempting to encode information on the radio transmission, and then you're attempting to receive it at the receiver and demodulate it. And those demodulation circuits exhibit all the same kinds of effects. And if you want to change the kind of modulation you're doing, well, you know, you have to be able to switch in a different stage. So, you know, very often you can switch an amplitude modulation stage in for a frequency, modulation stage, narrowband frequency FM, for example. That has its limits, and our mathematical ideas about how to encode information have progressed tremendously. And it allows us to encode information in very complex, clever ways, faster ways even, and that is very difficult to handle in the analog.
Eventually, most of the copper sulfate would be consumed, and the copper cathode will start electrolyzing water
and it
and
really
generating hydrogen rather than depositing more
started to
copper.
show up as
I
a
actually
software
recommend
radio
stopping early
concept.
when most of the copper sulfate
About
has been dissolved,
1984
but not
was when it really started to show up as software radio.
when there is
Digital
very little copper
receivers, the idea of
we
attaching
deposit copper
digitizers and computers to radio systems predates this. In the software radio world, the communications world, most people think of this showing up in 1970 from TRW. I will argue in a little bit that actually the radio astronomers were doing all the fundamental structures of the modern software radio about a few years earlier. Not a lot earlier, but a few years earlier. It's very contemporaneous with this. You have the idea, though, what if I took a lot of that analog electronics and implemented it digitally? And this at some level can happen on transmission or on reception. On reception here you have something where you have an antenna. You have to have that physical transducer into the electromagnetic environment that allows you to efficiently couple the electromagnetic wave. And it also provides antennas are a whole topic in themselves, so that's another complete talk. But and you can just go on and on and on if you really love antennas. But then you have some sort of RF analog stages. These can be filters, these can be translation,
early systems like a direct connection receiver, we have a diode detector of some kind, a bandpass filter, and the energy for the detection came from the radio wave.
And for a while it looked like
crystal radios. You can go get a nice kit
radio, everyone was very focused on the idea of
some headphones. You can in fact hear AM broadcasts because AM broadcasts are still going on from when they started early on, and they're very powerful, and they have enough energy that you can actually hear it when you do this.
We had someone who came back and follow-up paper, and they described ours as, well, this may be the first pure implementation of the software radio concept, and for radar, and I was really thrilled by that. But on the other hand, what's happened actually is it's too expensive to do that still for everything, and so we have seen what I would call the rebirth of analog radios as part of the digital radios. So you had military and government systems, and there were many systems with data acquisition and signal processing. The whole birth of signal processing as a real-time application to digital signals, where bandwidths have just increased and increased, has gone with this. And this digital revolution is underlying this, is the ability to make these wonderful computers and integrated circuits and chips that allow us to do this. Now, early on, the idea was, can we replace some of these analog stages, and in particular the demodulation? Can we actually go in and change the mode of the radio? So say, you've got a military radio and you've got to talk to 3 different types of platforms, and you can have one platform that you just tell it what to do, and it does it. This idea really was reinvented by Joseph Mottola, and Joe's down at Virginia Tech right now, and actually I had the pleasure of hosting him for a visit to Haystack at one point, and we got to talking a lot about these systems. But that was a rebirth of this idea. There was a lot of this going on in the DoD and the classified world, and actually the scientific world had a tremendous amount of digital analog hybrid combination systems where there was real-time signal processing going on. And Joe came along and kind of redefined all this and said, look, this is software radio and we can do this. And he was I can't even see my eye chart down here. This is Moore's law. This is early computers. This is where we are now, and this is the future of quantum computing and DNA computing and anything you want to do for computing, all right? You do the software radio with computing. And this is actually an important thing, is software You can have software-defined capabilities and modes. You can have software-realized instrumentation. You can have software radio that realize the signal processing for the entire radio on a chip. You can have multiple software radios that you bring together for joint processing, and you realize instrumentation from the composite of those radio systems. So the ensemble of radios becomes the instrument.
But also the copper as well.
Now, the real term software-defined radio showed up in 1995 from Stephen Bluss, and this is about the time I started doing stuff with what looked like software radars of various types. But analog radios, can be more or less complex, and in particular, the software complexity is actually vastly exceeding in many ways the hardware complexity at a very fundamental level, and we're able to build systems that have multiple modes. I mean, in scientific research, often you want one mode and you never want to touch it and you want to calibrate it, and then you can understand it there's one mode. If the system is dynamically switching between 600 different modes to optimize for something, it may be incomprehensible to a human being what's coming out, even though it might be optimal by some criteria. The other thing is that this computing, we have had a progression from ASICs to FPGAs to DSPs to GPUs to CPUs, or some hybrid combination. These are merging now. The FPGA DSP merger has kind of occurred, and there's going to be more computing. As people come up with clever ways to do incredibly high performance computing of various types, you can make software radios that use whatever kind of computer you want, and that's something people often forget. People often think, FPGAs are where software radio is today. Yeah, for the moment.
Software.
And it's not actually the important part of the software radio. It's the mathematics and the computing. And the idea that we can do that is far more important.
Click on the SPI server network.
One of the other things that has happened is software radios.
I'm going to click on these three little dots.
That is, power consumption can be.
It allows me to browse the SPI server network.
That is a challenge for everyone to overcome, and there's been great progress. We've gone
and
from
here's all the different.
To 100 watts. That's a factor of 10. That's pretty good. But it'd be nice to be down at a watt for a lot of systems, and that's challenging. Another thing that's very, very important for scientific applications, some kinds of applications, is you can keep the bits around of a software radio. So once you couple into the digital world, the information domain, instead of, in contrast to an analog system where the coupling is via an audio output to a human being, or maybe even to some signal processing that reduces data in real time, we can take that radio signal received, digitize it, bring it into a computer, and we can manipulate it and keep it around. We can keep it around for a short time. We're starting to be able to build systems that for narrow bandwidth and keep data for the life of the instrument. And that's very important, for example, for radio astronomy systems, for instruments that could observe the space environment. We begin to have a tremendous amount of information stored at the software radios. And we actually often have more limited bandwidth into them. And it becomes a problem of how do you find what you want that's interesting in this data buffer that has been accumulated. Early software radios, well, I'm biased. I'll show you, this is widely considered the first true software radio. This is Speakeasy from 1991. It was a Air Force project, and the idea was how to make those military radios communicate to each other at different modulations. This is the Midas 1 software radar, which was the actual software radar implemented up at NBC and it's real-time processing for those people who know transceiver
Obviously, the president taking time out of his schedule here to get a bunch of pictures, as he normally does. This is very typical to what President Trump gets when he goes to events like this. Very much. There we go, taking a few more pictures.
Because his notes are wonderful and very scary to me as an engineer who kind of knew what he was doing. Going, oh God, I got to get rid of this and replace all this. This custom hardware era. This is the VLB Mark I system, 1967. It has
221 status, all units.
Clock that's not there.
You hold ours for now.
Actually incredibly important to using software radios together. So if you want to use more than one radio together, the ease with which you can do it is actually dominated by the
527 status.
And so here you had a hydrogen maser, one of the most stable clocks we can create. We're starting to make things like optical lattice clocks that are better. You have a computer and a data acquisition system. There's obviously some test equipment to monitor what's going on, and a data recording device, tape. And you shouldn't underestimate the power of these tapes if you load a 747 full of the tapes and fly it somewhere. Is you can transport an incredible amount of data. And up until maybe about a decade ago, this is how radio astronomy moved wideband data around the world. Now they do it with hard drives. Soon it will be SSDs. It's actually vastly simpler to move
527 status
than it is to get network bandwidth that are reliable across the distances involved, which are the whole planet in general these days. But this system is, from my point of view, I realized at a certain point that all the radios I was implementing were in fact very similar to the early VLBI systems for interferometry that the astronomy community had admitted. Another thing that came along then after the custom hardware era, these were defense and scientific systems. They were expensive. Was what I call the ASIP, application-specific integrated circuit chip. This is where you have proprietary chips that were developed. There were several of them. Analog Devices had one. Harris had one. This is a company called Gray Chip, which was eventually bought by Texas.
Including the types of components in demand, preferred payment methods, and the logistical challenges of shipping globally. DOS website development, building a platform that is easy to navigate, provides detailed information about each component, and offers secure payment gateways. Incorporating SEO strategies to enhance visibility is also crucial. 3. Logistics and supply chain management, establishing reliable partnerships with suppliers and logistics providers to ensure a steady supply of components and efficient delivery.
And that precipitates out the cobalt hydroxide as quite an insoluble solid once again. And we end up with potassium and lithium in solution. The idea then, once we have potassium ions and lithium ions in solution, we can push the pH up a bit with hydrochloric acid, boil it to dryness, so we both have potassium chloride and lithium chloride, and then we use ethanol to extract the lithium chloride, because lithium chloride is quite odd in the sense that it has quite a high solubility in ethanol, whereas potassium chloride, sodium chloride, they have
hot beaker directly onto my scale, so I'll let it cool down some, and then I'll give it another way.
And it's a precursor to the effect of software radio on astronomy, which I'll touch only briefly on later. This is what I was working on in 2000, 2001. It was the Midas W software radar system's Millstone data acquisition system.
So we lost about 0.56 grams from heating, so it was almost dry, but it was worth doing. But I still don't know the exact weight of the calcium nitrate because I don't know the weight of the beaker. So I'll have to solve that. That shouldn't be very hard.
Software radar system where actually almost even the digital down conversion beyond an initial down convert was done in software and in general purpose software written in largely C and then later Python and C. Modern software radios is where we have come to now, and modern software radios have become actually incredibly low cost. The RTL software radio dongles, people made a digital.
So after having washed and thoroughly dried the beaker, I'll get a dry weight.
And they put a test mode into it that put out
160.75
with the phase information preserved with the voltages, and these things started to show up to $15 or $20. And we've done actually a lot of science with these for student projects, for demonstrations, for building systems that are inexpensive per channel. And it's actually kind of incredible if you spend some time trying to calibrate the things and use them, how well you can do. And you do, as I mentioned, have to have a computer plugged into it. And the computers for a long time, the best get is a $1,000 laptop or $700 laptop. You can get that down now into the few $100 computer if you're willing to live with the performance. Largely these systems that have come about, it's high performance computing, amazing ADCs and DACs. And then there's been an effort, an industry effort to create very highly capable,
and a lot more power because the switching rates in the electronics are much, much higher. Radio's cost. I mean, we're going from $10 to $10,000 end, $10 end for the RTL dongle. There are corresponding differences in performance often in the radios. They have really different characteristics in how they accept clocks, in dynamic range, in their production of spurious signals, which I'll talk a little bit about. Underneath this, these radios change almost daily. We're about to have a lot of Xilinx RF system on a chip showing up. They're going to knock the per channel cost down eventually. The radio isn't the important part. This is going to change. We're going to figure out how to get rid of these, integrate them with things. Some applications, maybe we'll grow them in trees at some point. But nevertheless, the software, the information,
the Dapper, making mine smell like beef fat,
democratization of software
buffet platter, beef, buffet platter. Come on, my stick. Yes, you got the cold water spatter from the beef buffet platter.
These are up into the 300 megahertz range.
Dapper always riding on the
radios. This is actually a
kicking your ass to the sea. Kicking your ass.
Digitization and streaming. Now, the thing that happened is the power went up. We're ending up at 10 to 80 watts per unit. Per channel, it's still fairly close to the gray chip, but and then you add a computer. Now, the computers I'm using are usually between 15 and 40 watts. 40 watts gets you a very high performance. 15 you have to live with bandwidth limitations. But this is, combined power levels of 25 to 120 watts. It's still limiting. I've got a project I'll talk about that's solar and battery powered. It's a distributed system, and it's actually very hard to deal with these power levels in the instrumentation. You have the return of the tuner in the modern software radio. So this is to allow you to use less expensive digital electronics, and in particular, if you take the gigasample per second radios and you try to do all your software radio with them, you can burn a lot more power.
What you wanted, but the chipset electric is waiting just for you.
Radios cost. I mean, we're going from $10 to $10,000 end, $10 end for the RTL dongle.
So with the paper cut, Cowboys lie.
They have really different characteristics.
Done more for the black community than any other president since Abraham Lincoln, and maybe including Abraham Lincoln, frankly, but since Abraham Lincoln. And it looks like our polling is very good in the state of Georgia overall, so we're very happy about it. But we've had, you see the support, it's been really something special.
Thank you.
Thank
Who you got for the Masters, Mr. President? The Masters. Who you got for one of the Masters?
I have a lot of guys. They're all friends of mine. Every one of those players is a friend of mine, so I better not pick. But you have some great ones, and you're going to have some. It's going to be some competition. You're going to have some. Dustin's been great.
Information structures behind this are actually what's important, and understanding that those patterns and architecture.
Well, it's all dissolved, but it's cloudy. I don't know why, but
is actually more important.
I'm going to proceed anyway. So I'm going to put a watch glass on top, and as I said before, this is cool at room temperature. And I'm going to slowly add the sulfuric acid.
Of time is varying in amplitude, and we want to digitize it, and we're going to quantize it into specific levels. And if we have a perfect AD converter, things so that they're linear over a large range, and so that they're not producing false signals, except where we know they're doing it at some level, because they all actually lie to us at some levels, because digitization isn't perfect. I mean, sometimes there are errors. Sometimes the signal is fluctuating in a way where we're not sampling all the energy. So if you have something that's, if this is frequency and this is the Nyquist zone of your A to D converter that you're digitizing here, and you have a lot of energy going on at higher frequencies, well, guess what? There's aliasing. It all comes down and folds down, and this is what you see in your software radio. Isn't it fun? You can try to figure out whether you're seeing what you want there. Now, you can do better. You can filter all this, make it very clean. You can actually put the energy in a given Nyquist zone. Modern ADD converters, can actually, what is called subsampling signals. They can pick up signals that are varying at higher frequencies, and as long as the bandwidth of the signal is narrow enough, you're still oversampling it in a Nyquist sense. And this will fold down in the aliasing, and lo and behold, you can get a nice spectrum out of what you wanted to measure. The other thing that's going on here is, anything you do to this signal, once you've digitized it digitally, can introduce effects like this. So you have to often do frequency selectivity in digital signal processing. Well, okay, there's a numeric oscillator associated with that. That numeric oscillator has some, quantization. It's got some dynamic range. It's got spurious components, all of which are going to get combined with the input information from the radio signal that you digitized to confuse you, cause you trouble, and generally make things less linear and less ideal than we'd really like. Oscillators and clocks, it turns out, are critical to this process. The analog to digital converters and digital analog converters are doing these digitizations on periodic boundaries. And that periodicity is very critical to the performance of the radios often. In fact, a lot of the systems that we build are often clock limited in their actual performance for their application. As you start to look, for example, at radio astronomy systems where you want to look and compare signals from different locations together in order to make a phase measurement to do interferometry. And when you do that, what you can find out is, well, as you go at higher and higher frequency, you need better and better clock stability and better, in terms of the phase noise of the clock, for example, in order to actually make the measurement and get the information out that you really wanted to. Nyquist sampling, I mentioned, is the common approach. It's not the only approach. Fourier analysis in general is one approach for fitting information at that's a signal of some type. You can use other basis sets. You can use other approaches. You can do model-based fitting in the A to D converters, for example. There's a whole area of compressive sensing, for example, that came out of this idea. Well, I got this gigasample converter and it's eating a lot of energy, but I'm measuring something that has a kilohertz of process bandwidth for the information. That seems really inefficient. I'm taking billions and going down to kilohertz. Can I do away with that? And that's still a question in software radios, I think, is how can we do many of the things we want to do without the gigasamples necessarily? Alias sampling, subsampling is used in many systems. I built systems that subsample, for example. And this ADC performance under this, we've got marvelous converters today. They're just beautiful devices. Even in the last decade, or actually the last few years, they're taking incredible strides. Now, once you've digitized this information, you're going to do some software radio on it. You want to do that frequency selectivity I mentioned. And so we're going to do digital down conversion. So one of the things we're doing, and I was told you actually, if you've seen the last series in the series, you were told all about IQ modulation and detection, and so you know something about it, hopefully. But the basic idea is that in the world around us, when we have a radio signal, when we digitize that voltage, it isn't enough to just know amplitude. We often want to know phase relative to some arbitrary point we define, and we want to know how that phase of those radio signals varies. And one of the reasons is we can use phase to encode information. We can use it usefully. We can use it to voltages from a system as complex numbers. And very often voltages actually, when you get down to it, don't actually have real information. What you want are power-like quantities. You want products of voltages. Whether it's for astronomy or whether you're looking at the power, the signal-to-noise ratio, for example, and you want to estimate the power in a system, you're often not actually wanting to take complex products of the voltages. When we do this digitally, or you can do this in an analog radio if you want, we're going to have some local oscillator. This is the super heterodyne type of principle again. And then we're going to take and we're going to mix the signals and do some filtering on them. In this case, we'll do some digital filtering. And we've got this mixing process where we have an in-phase component and a quadrature component, and the relationship between those two is the complex phasor of the voltage, and it tells us the phase relationship of that signal relative to this clock we feed it. This is where another clock comes in. It comes in as the numeric oscillator. For example, if you want to build a coherent system, it isn't enough just to have a coherent clock for the analog components. You actually need to make sure the numeric oscillators line up. And when you want to start taking data in two systems that actually need to know the phase relative to each other, you have to align all those numeric oscillators, and you need to start them at the same moment. It's not always trivial. And then you're going to do some decimation. This is where you're going to frequency select your signals. This is not the only way to achieve frequency selectivity. There is, of course, multi-rate signal processing where you can do polyphase filter banks, other kinds of filter banks to do this type of frequency selectivity. But we want to achieve that in order to get the channels of the radio signals out, to limit the output data rates and the bandwidth that the subsequent signal processing is going to handle. sometimes you build systems that handle little bursts of data and you're going to decimate in time. Other times we often build systems because it makes synchronization easier.